In this video, you'll learn everything about earthquake loads with respect to STAAD Pro. So we'll be learning about defining the seismic parameters, we'll be applying earthquake loads, we'll be analyzing the structure, and we'll be comparing our results with the manual calculations. So without any further ado, let's get going. Hello and welcome. If you're new to this channel, do consider subscribing and hitting that notification bell. Also, if you are not already a member of our private Facebook group, go to the link in the description below and join our Facebook group. Also, check out my second channel, which is called the Binary IQ, where I share different kind of technical stuff like web designing, graphic designing, video editing, and many things of the same nature. I'm very hopeful that you like that channel as well. Do support me there too. And with that said, let's get going. Now, if you have not watched my previous video on earthquake loads, do check that out. In this video, I'll be going deep into the load application and analysis using STAAD Pro. But if you do not have the basics clear, there is no point using a software. In this video, I have gone into a lot of detail about the static analysis of earthquake loads, and I'm very hopeful that you will like that video. And in some ways, it is a prerequisite so that you can understand this video. However, if you have already done that, let's get going. Now, as per my previous video, we did the analysis as per IS 1893 using what is called the static analysis method, and we'll be following up with that. So in this video, we'll be doing the static analysis method, but instead of doing it manually, we'll be using the STAAD Pro software. This was the problem statement from our previous video, and we'll be going on from there. So let's start off with the first step, that is creating a structure. So I'll take you inside STAAD now, and we'll be creating this structure. We'll be modeling this structure. If you haven't watched my previous video, I'll link some videos which you can watch if you don't know how to create a structure. So let's get going. So here I am inside a blank file in STAAD Pro. Now, instead of creating this structure on a node to node basis, because it is a very symmetric structure, we can simply use the structure wizard. I have talked about this in my previous videos. You can check those out. So what I'll do is go to where it says geometry, go to where it says run structure wizard, click on it. Here in the model type, I'll hit the drop down, select frame models. I'll just hold the bay frame, drag it on to our creation window. Now let's check out the length, height, and width first. So we are going to create this structure. We have a length of 4 spans of 5 meters each, that is 20 meters. We have a width of 3 spans of 5 meters each, that is 15 meters. And we have a complete height of 13.8 meters with different floor levels. So we have a 4.2, 3.2, 3.2, and 3.2. So let's create this structure using our structure wizard. So we have a length of 20 meters. So I'll just put in a 20. In the number of bays, we had 4 bays. So it will equally divide it into 4 parts. You can simply click on these 3 dots to even confirm that. So we have 5 meters each. That is good enough. I'll first select the width. I'll change it to 15. In this case, we had 3 spans of 5 meters each. So I'll just put in a 3, check it with the dot again. So we have 3 spans of 5 meters each. And finally, the height was 13.8. And in this case, the bays were 4 numbers. However, the spans were not equally divided. So we'll change that. The first floor was 4.2 meters. The second floor was 3.2. The third floor was 3.2. And the final height was 3.2 again. So I'll just click on OK. Always be sure that the summation here should be the same as the summation here. Otherwise, it will give you an error. So I'll just click on apply. So we have our structure built. Let's transfer it onto our file. In order to transfer it, you can simply click where it says transfer model, or you can go to where it says file, click on merge model with STAAD Pro. So either ways, it works the same. So now it's asking me, would you like to transfer? Yes, I do. It wants me to define the XYZ location as to where I'm going to paste it. So I'll stick with the origin, that is 0, 0, and 0. So I'll just click on OK. We have a model done. I'll just click out of this snap node beam because I don't need the grid anymore. Now, in order to confirm that we have done it correctly, we can simply use this display node to node distance. So we can see the length as 20 meters. We can see the width as 15 meters. And we can in fact see the complete height as 13.8 meters with each floor being different. So this floor is 4.2. This floor is 3.2. This floor is 3.2. And the final one is 3.2 again. So just like that, we have our structure ready. Let's get rid of these distances. Now I've talked about the creation part. I'm not going into that. So I simply will go into the general. I'll go into the property tab. I'll click on define. I'll simply create a rectangular structure. I'm not much worried about the dimensions because we are not going to design it for now. We are just going to analyze it. So I'll just click on add. I'll just click on close. With this section selected, I'll click on assign to view and assign it to all the members which you can see. So I'll just click on yes. So just like that, we have a structure assigned. Always right click and go to 3D rendering to see that all the sections have been applied to each of the members. With this step done, let's click on support. We'll be creating a new support. So I'll click on create. Again, I have a video on creating supports, so you can check that out. I'll choose a fixed support, click on add. I'll select the support, go to the front view, select all these nodes. Now in order to check if I've selected all these nodes, I'll go back to the isometric view. And you can see I've selected all the nodes properly. In the assignment method, I'll select this assign to selected nodes, click on assign and click on yes. So now I have my structure done and the supports done. Now let's move on to the best part, that is the load definitions. So let's click on load definitions. Now when it comes to earthquake loads, we do our entire process in 2 steps. So the first part involves definition of the seismic loads and the seismic parameters, and the second is creating a load case with respect to those parameters. So let me walk you through it so that you understand it better. So the first step is to click on this plus icon inside definitions, move to where it says seismic definitions, click on it. With this selected, go to where it says add, click on add, and here we get the options of defining our seismic parameters. So let's start off with first defining the type. Now in this case, we'll be selecting our code. The code which we will be using is IS1893. Now I have a previous version of STAAD, so the 2016 update is not available. However, even the 2002 version will work because there have not been too many changes, and any changes which have been there, you can override it manually as well. So I'll just click on Indian IS1893 2002-2005 version. With that clicked, you have different parameters which you can fill in. However, there is a very handy button out here which says generate. You can click on it. Once you click on it, you'll get this window where you can define all the properties. So let's check what our properties were first so that we can fill it out here. So these are the building properties. The building type was office building. The location was in Shillong, which is in Meghalaya. The soil was medium stiff and the structure type was RC frame structure. So in the manual method, we had to go through what is called the static analysis method. In that, we needed to find this design base shear, which is called VB. Don't worry about all these. The main thing was to find this AH value, which is a coefficient. So basically this entire equation is nothing but the weight of the building multiplied by some coefficient, which gives the value of the horizontal force which you need. So this is the force we are looking for. For the first step, we need the AH. So we calculate AH using this huge formula, which I broke down in my previous video. And ultimately we got these values. We got a Z value of 0.36, which corresponds to the zone 5. We got an SA by G value. We got a response reduction factor of 5, which corresponds to a special moment resisting frame. And we got the importance factor as 1. So we will be using these values in our STAAD parameters. Let's go back. So out here, instead of choosing it from the city, because right now, if you go through, you do not have Shillong available in this code, because again, it is not an updated STAAD version. So instead of choosing it by city, I'll simply choose it by zone, and the zone, I'll select it as 5. So as soon as I select the 5th zone, you can see the Z value as 0.36. Now the response reduction factor in our case was 5. I have talked about why it was 5, even though the building is simply defined as an RC frame structure. This is primarily because as per IS 1893, if you have a structure which falls in zone 3, 4 or 5 and it is an RC frame structure, you have to use the ductile detailing, which ultimately corresponds to the structure becoming a special moment resisting frame, that is SMRF, which has R value of 5. So that is why we are selecting this special moment resisting frame. When it comes to the importance factor, in the previous code, we just had 2 importance factors. That is, one was for important buildings of 1.5 and the other was for all the other buildings as 1.0. In the latest revision, as I talked about in the previous video, there is one more category of 1.2. However, we are not worried about that because our case was an office building, which has an importance factor of 1. In the rock and soil type, we have a medium soil, and in the structure type, we have a simple RC frame building instead of a steel frame. So I'll just select that. The damping ratio by default is 5%, and that is what IS 1893 recommends. So with all these selected, let's simply click on generate, and that fills in the value out here. So if you know the values, you can simply put it from here, but it's a good idea to go from generate because that is much more intuitive to use. With these parameters done, we'll simply click on add. Once you click on add, you can see on the right side, you have your parameters done. Now it is time to add your loads. Let's check out our loads. Let me get out of this first. So these are the loads given in the problem statement. So the dead load has been given for all floors to be 12 and for the roof to be 10. And the live loads on all the floors are given to be 4, and for the roof it has been given to be 1.5 kilonewton per meter square. So when it comes to the seismic weight, or the W of this equation, which is the seismic weight of the building, you have to pay attention to the IS code recommendation, which says we have to take the full dead load plus an appropriate amount of imposed load. So whatever dead load has been defined in this problem statement has to be completely taken on all the floors, because ultimately seismic load is nothing but the load which the building carries at the time of an earthquake. So the dead load is not going anywhere. So we will be taking that completely. However, when it comes to live load, the conditions change slightly. As per IS 1893, for loads up to and including 3 kilonewton per meter square, the percentage of imposed load to be considered is only 25%. However, when the imposed floor loads are greater than 3 kilonewton per meter square, we'll be considering 50% of that as our seismic weight. There is one more important thing to consider, that is the imposed load on the roof. As per the IS 1893 clause 7.3.2, you can see that the imposed load on roof need not be considered. So with these three ideas, that is the dead load being taken 100%, the imposed load up to 3 being 25% and greater than 3 being 50%, and finally no imposed load on the roof. Let's define our loads. First we'll be defining our dead loads. For all the floors, we have a 12 kilonewton per meter square load, and for the roof, we have a 10 kilonewton per meter square. So for this floor, and this floor, we have a value of 12, and for the final floor, we have the value of 10. So in order to add those loads, we'll again go inside seismic definition. We'll go inside our parameters, select it, click on add. Once you click on add, you'll get this window, and we are right now not going to add self weights because we are trying to compare our problem with the problem which we calculated in the previous video. In that, we just had floor weights. So I'll just click on floor weights. Now I have made a video on floor loads. However, when it comes to earthquake load definitions, just remember that wherever pressure is defined, there is no need to put a negative value. So that is one consideration you have to understand. So as per our problem statement, the dead loads on floors for the level 1, 2 and 3 is 12 kilonewton per meter square. So I'll just put in a value of 12. In the Y range, you can see the floor level starts from 4.2 and it goes all the way up to 10.6. So these are the three floors on which the load has to be applied. That is the load of 12 kilonewton. So the Y ranges will be from 4.2 to 10.6. So I'll put in a 4.2 and a maximum value of 10.6. Let's click on add. Now for the roof, the value is 10 kilonewton and the roof Y range is from 13.8 to 13.8. Again, if you're not getting what I'm talking about, do check out my video on floor loads and you'll have those concepts clear. So for the roof, I'll just change this value from 12 to 10. The minimum range is from 13.8 to 13.8. I'll just click on add. So with these two done, we have our dead loads done. Let's move on to the live loads. Now for all the floors, the live loads is 4 kilonewton per meter square. The value is greater than 3. So we'll be using 50% of this load. So 50% of 4 kilonewton per meter square is 2 kilonewton. That is what we will be using from 4.2 to 10.6 Y ranges. So we'll have a value of 2 kilonewton per meter square on this floor, on this floor, and on this floor. All will be having a value of 2. And when it comes to roof, you know that the imposed loads on roof need not be considered. So the value on the roof is going to be 0. And by the way, all these values are in kilonewton per meter square. So let's recreate it. So we'll have a value of 2 kilonewton per meter square as the live load on the Y ranges from 4.2 to 10.6. I'll just click on add and I'll close it. So I have my weights defined. However, when it comes to earthquake loads, there is a bit of difficulty in visualizing it because, for example, if I click on it, you won't be able to see what loads have been put here. And that is one thing which you have to consider, that you have to be very sure about what values you are putting in the X, Y, Z ranges and the pressure values. So do a bit of manual calculation yourself before starting on with the STAAD, because you will not be able to find the errors in your files or the issues with your file if you have something wrong going on, because it is not visually available for you to consider. So with these three done, we have defined our earthquake. So this is all about the definition part. As you can see, we are inside the definition. Now we have to apply this definition or this load on our structure. And in order to do that, what we will do is go to where it says load case details, click on it, click on add, and we'll create an earthquake load. So we'll simply call it earthquake load, but in the X direction. In the loading type, you can let it go, but I just like to keep things proper. So I'll just select the seismic, I'll click on add, and I'll create one more load which will be in the Z direction. So I'll just click on EL, and in the Z, I'll click on add again. So we have our two load cases done. Now we are not going with the Y because when it comes to earthquake loads, the Y forces on the structure are not that significant. So let's click on the ELX first, click on add. And here we'll be selecting our seismic loads. This is going to be our force in the X direction. So I'll just simply select the direction as X and we'll put in a factor of 1. I'll click on add and I'll click on close. Again, I'll go to where it says ELZ, do the same thing, click on add, go to seismic loads again. This time I'll select the Z direction and put in a factor of 1 again. And I'll click on add. We will not be worrying about all these because these are not necessary in this simple case of a building. Click on add, click on close. So we have defined our earthquake in the X and in the Z direction. Now, when you're creating a structure for a client and the structure is not this simple or symmetrical, it is a very good idea to create a separate load case for a negative X direction as well as a negative Z direction. So in case of unsymmetry, that is the way to go about it. However, I'll try to keep things simple here and we'll be working with simply an earthquake load in the X direction as well as in the Z direction. With these loads defined and the earthquake parameters defined, we have done our due diligence. Now let's move on to analyzing the structure. Now I have not talked about analysis in very much depth, but I'll be taking you through a simple step. So again, we move from top to down. So we'll click on analysis and print. In the print option, I'll just select all and I'll click on add. Let's click on close. I'm not going to be designing the structure. I'll be just analyzing the structure so that we get the load values and compare it to whatever we got from our manual analysis in the previous video. So with all these things done and being very hopeful that I have not messed anything up, let's go to analyze and click on run analysis. I'll just click on save and the analysis has been done. So let's click on view output file and click on done. So we'll just scroll down. So as you can see, our load definitions, we have an ELX direction and the ELZ direction, and we get our time periods and other values. So let me first take you to the solution which we did in our previous video. So these were the values which we got from our manual calculation. We got the AH value as 9% or 0.09. We got the W value as 15,600 kilonewtons. And we got our base shear or the design base shear as 1404 kilonewtons. Also, if you remember, we did not put in the SA by G value manually. However, we calculated this value in our manual calculation, which came out to be 2.5. So here we have the SA by G value as 2.5. We have our AH value as 0.09, which is 9%. And we have our total load as 15,600. So the VB as per 1893, which is the design base shear or the total lateral force, this comes out to be 1404 kilonewton, which is exactly the same as we calculated manually. Of course, the same thing comes for the Z direction as well, because if you remember in our previous video, the SA by G value in the Z direction was 2.5 as well. Thereby, everything remains the same and we get the VB value in the Z direction to be the same, that is 0.09, which is the AH value, and 15,600, which is our W value, giving us a VB value of 1404 kilonewton. So we get our VB perfectly. However, this is just the total lateral force on the structure. What we need to do is break this force into different floor levels, which we again did in our previous video. And we use this crazy formula to find it, which is nothing but your VB values multiplied by some kind of a coefficient. So some kind of percentage values ranging from 0 to 100%. And we did calculate it using this chart. And let's find out what we did. So in the first floor, you can see our values come out to be 77.21 kilonewton, which is a 6% Ki value. That is 6% of this entire 1404 came out to be 77. So let's check whether we did it correctly. If we move down, this is our first floor levels, and you can see the total values coming out to be 77.205, which is 77.21. At the level 4.2 meters. At the level of 4.2 meters, we had a value of 77.21, which is absolutely perfect out here. Let's move on to the next level, which is 7.4 meter height. We get a value of 239.669. So at the level of 7.4 meters, we got a value of 239.67, which is exactly the same. Let's move on to the next floor, which is the floor at 10.6 meter height. We got a value of 491.768, which is basically 491.77. And at 10.6 meter, you can see the value as 491.77. Finally, at 13.8 meter height, we get a value of 595.358, which is 595.36 if you round it. And at 13.8, we get the value of 595.36, which is absolutely perfect. So as you can see, the values which we get are precise to the second decimal point. And that is an extraordinary thing to see when it comes to manual calculation of earthquake loads. And this is one very important lesson when it comes to using any software in general, that you have to understand the manual calculation aspect of it and then use those manual outputs to verify what you're doing on your actual structure or your actual calculation part using the software itself. Because ultimately, a software does not have its own brain. Whatever you feed into it, you'll get out of it. So if you feed garbage in, you'll get garbage out. If you feed valuable information in, you'll get the valuable information out. So always pay attention to that. Now, if we move down, we have the same values in the Z direction as well, which will exactly be the same. So I'm not going into that. I'll just click out of this output file. So we are done defining our structure. Let me go to the front view for a minute. So we know that the values at the floor level of 4.2 is 77.21. So we know that the floor values here is going to be 77.21. Now, how do we verify it visually? Once you're done with the analysis, you can simply go to General again, go to Load Definition, go to Load Case Details again, and select or click on the load in the X direction. So we are right now in the X direction. So you get all these arrows. Now these are, if I zoom out of it, you can see the arrows are a bit too long. So let's scale that properly. In order to scale, I'll just simply right click, go to labels. I'll go to where it says scale, I'll move that out a little bit. In the point force, I'll just start increasing it and I'll leave this apply immediately checked on. So I'll just increase this so that the arrows become smaller and it's much easier to view. So I think this much is good enough. I'll increase it slightly and I'll click on apply and click on OK. Let's go to the isometric view and you can see all the arrows are visible. I'll go to the front view again. Now I just want to pay attention to this zone here, or rather only this floor, but I'll just select all these, go to view selected objects only. I have talked about all the view options and most of the things I'm doing. That's why I'm going through them very quickly. If you have any confusion, do check out my previous videos and you'll get all the information out there. So I'll just go to isometric view again. However, I cannot see the value of the loads right now. So what I'll do is right click again, go to labels again, and this time I'll go to where it says loading display options. I'll select load values. I'll select it and I'll click on OK. Just like that, we can see all our values right here. Now in our manual calculation, what we did was calculate the total load which is coming at this particular floor level. However, STAAD takes it one step further and divides that complete load into different nodes, onto different nodes. And you can see the division here. Now, if you're not sure that the values are coming to be exactly the same, I'll verify that for you. So I simply have an Excel file here. So let's start from the corners. We have a value of 1.608 and we have 4 of these nodes. So as you can see, the greater number of nodes take a greater number of loads. So with a node having 4 joints on it is taking a lot of load compared to the one which has 3 compared to which has only 2. So 1.608, we have 4 such nodes taking this value. The next value of 3.217, that is being taken up by 1, 2, 3 and 4, 5, 6, 7, 8, 9, 10 values. So we have 10 of these. And finally, we have a value of 6.434, which is being taken by 1, 2, 3 and 3, 6. So let's simply multiply both of these. And I'll copy the same formula. Let's do an auto sum. As you can see, we get the same value of 77.206, which is 77.21, which is exactly the same. So this way you can analyze your structure very simply. Now, if I click on ELZ direction, you'll see the load in the Z direction as well. So in this video, we defined our seismic parameters. We first defined our zone, the R values, the I values, and so on. And we defined our flow weights or the loading on our building. Next, we created earthquake loads and we did an analysis to get the same values which we get by the manual calculation. So I hope you liked this video, and if you did, do not forget to hit that like button. Also, do leave a feedback as to what you want to see next. Again, if you're not already a member of this STAAD group, do join it. I'll leave the link in the description. And finally, do support this channel by sharing the videos and the channel itself with your friends. Also, do check out our other channel, the Binary IQ. I'm very hopeful that you'll learn some valuable stuff out there too. Thank you for watching, and I'll see you on the next video.